Hello students, in lecture 16 of your course Elements of Discrete Mathematics, here we shall discuss two types of graphs. One is the Eulerian graph. In Eulerian graph we will study Eulerian circuit, Eulerian path. Hamiltonian path is the another kind of path or graphs are there. In fact, about Euler graph and Euler line, we have given you the idea from where this problem was uh, generated. That was the Königsberg's bridge problem that we have discussed in our earlier lecture. So, certain more aspects of the Euler graphs we are going to discuss here. The first thing is Euler circuit. What is an Euler circuit? An Euler circuit is a cycle of an undirected graph, graph that traverses every edge of the graph exactly once. That means every edge of graph is traversed exactly once and ends at the same node from which it began. So in fact, the Königsberg's bridge problem was to obtain an Euler circuit, but that was not possible. The solution was given by Euler. An Euler circuit is also called an Euler line. Now a graph that consists an Euler line is called an Euler graph. So the Euler line, Euler circuits, we are going to discuss in detail with the help of an example. Certain remarks are there. An Euler graph is always connected. Remember this. A disconnected graph cannot be an Euler graph. A connected graph is Euler graph if and only if it can be decomposed into circuits. If and only if it can be decomposed into circuits. So let us see one example of an Euler line, or you can say the Euler graph here. Just look at this graph. 5 vertices are there in this graph, and the vertices are denoted by A, B, C, D and E. Suppose I denote this edge AB by E1, this is by E2, then this as by E3, E4, E5 and here is E6. Now let us see, can we find an Euler line or Euler circuit in this graph starting from one vertex? Let us start from this vertex A. When we are starting from this vertex, along the edge, along the edge E1, then I write it. I am starting from A, then along the edge E1. Of course, when we are traversing through E1, we have to move to the vertex B also. So I'm writing it B here. Now from B, suppose we further traverse along the edge E2. So I write here E2. Now along the edge E2 when we are traversing, so here we can have this vertex C. So I should write here C. Now from C, we have three choices. Either we can travel through E6, we can traverse through E5, or we can traverse through E3. We have three choices. But if I go back to A along this E6, then it will not solve our problem. That means we will not be having an Euler line because these edges will be left untraversed. So that way we have to move either through E5 or through E3. Suppose I am traversing through this E3. So from C I am traversing through E3. So I have to write here E3. When I am traversing through E3, I am arriving at D. So write here D. Then from D we should move along E4. So I am writing here E4. Then from E4, along E4, I am arriving at suppose E. So write here E. Then from E, now we have to return back through E5. So I'm writing here E5. Now, after traversing through E5, we arrive at point C, suppose, at vertex C. Now again at vertex C, we have two choices, either to go back through E2 or we should move along E6. But if we go back through E2, then this edge will be traversed two times because we have already traversed through this edge E2. So that way we shall not go back through E2, but we should go along E6. That means after arriving through E5 at the vertex C, we should move along E6 and finally we return to the same vertex A from where we have started. So now in this journey, what had happened? Just you notice the things here. We started from this vertex. This is the 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 vertex, and this is the vertex. So initial and final vertex is same. And in this journey, we have traversed through each of the edges exactly once. You can say, you can see here that the edge E1 is appearing once, E2 is appearing once, E3 is appearing once, E4 is appearing once, E5 is also appearing once, and E6 is also appearing once. But here you can see one vertex is repeated. That means we have traversed through the vertex C twice. Vertex C has been traversed two times, once when between E2 to E3, and then again when we have returned, we have again went through this vertex C. So in an Euler line, in fact, this whole description denotes an Euler line, or you can say the Euler circuit. Euler line. So I think the idea of Euler line or Euler circuit is clear with this example, and the whole graph can also be known as an Euler graph. Euler graph. In fact, if you can find an Euler line, then that graph is called an Euler graph here. So in this case, you have noticed that in an Euler line, every edge is traversed exactly once, but a vertex may appear twice. So whenever you are asked to describe an Euler line, then you should write the Euler line in this manner. Now see another examples. Both of these two examples are Euler graphs. You can see in these Euler graphs you can find an Euler line. And in fact here you can see with the help of Euler's theorem that degree of each of the vertex in these two graphs, these two graphs is even. Therefore these two are the Euler graphs. And even you can also find some Euler line and these graphs. In fact if you start from any of the vertex, after passing through or traversing through all the edges exactly once, you can also return back to the same vertex by some manner. So you can find the Euler line. Suppose if I mark these vertices in this manner, suppose this is V1, this is V2, V3, V4, V5, V6, V7, V8, V9, V10, V11. And then if you start marking the edges, then you can also mark the edges like this E1, this E2. E1 is from V1 to V3, E2 is from V1 1 to V2, and let this is E3. You can say this is E4, E5. I can say this is E6, E7, and let this is E8, E9, E10, E11, E12 that join these two vertices. This is E12, and let this is E13, E14, E15. Let this edge from V4 to this V8 is E16, and then what is left here? Let this is E17. So I think I have written all the vertices and edges here. Then from this graph, you can find an Euler line, or you can find an Euler circuit there. So how you can describe? You can describe in the same manner as is done in this case. This was the simple example here. Then some more complicated Euler lines can be there. So in fact, definitely here you will see that in fact this is V1, V3, 4, and 5. Okay, so here you can see that due to Euler's theorem, you can conclude here that degree of each of the vertex is even. So definitely it will happen that you will start from V1, and after traversing through all the edges exactly once, you will definitely return to V1. So let us try to find the Euler circuit here. Euler circuit here. And the procedure I have explained in the earlier example. You start it from V1. Suppose I start at V1, and I mentioned that it was is E1 and this is E2. So V1 to suppose you are having E1, then V3, then we are having suppose E3, like that, E3 to then we are going to V2, and in this manner you can find the Euler circuit. You try to write it down. Similarly, mark the vertices in this case also. Let this is V1, this is V2, this is V3, V4, V5, and similarly mark the edges, and then try to find out the Euler circuit here. Next is the Hamiltonian circuit. You know, in an Euler line, as I have explained with the help of example of a connected graph, an Euler line of a connected graph is characterized by the property of being a closed walk, because you return back to the same vertex from where you start. So an Euler line of a connected graph is characterized by the property of being a closed walk that traverses every edge of the graph exactly once. Edge is traversed exactly once. As I explained, vertex may appear more than once. But in a Hamiltonian circuit, in a connected graph, is defined as a closed walk that traverses every vertex of the graph G exactly once, except the starting vertex. Only starting vertex will be repeated because you have to complete the circuit. Otherwise, each vertex will appear exactly once. So in this regard, if I say that the earlier one, this uh, Euler line is there, but this is not a Hamiltonian circuit. This is definitely a Euler circuit as I have explained here, but it is not a Hamiltonian circuit because in this case the vertex C is traversed two times. However, the initial vertex will be repeated, but in between also the vertex C is repeated. Vertex C has been traversed twice. Therefore, this is not a Hamiltonian circuit. In fact, it is the Euler circuit only. So this is the difference between the Euler line, Euler circuit here, with this Hamiltonian circuit. Now let us see this remark. A circuit in a connected graph G is said to be Hamiltonian if it includes every vertex of G. Hence, a Hamiltonian circuit in a graph of n vertices consists of exactly n edges. This is the point to be noted. A Hamiltonian circuit in a graph of n vertices consists of exactly n edges. So these are the examples of the Hamiltonian circuits. Here one vertex V is marked. When you are starting from this vertex, you can see in total how many vertices are there? 1, 2, 3, 4, 5, 6, 7, 8 vertices are there. And these arrows, if you are traversing, you are starting from this vertex V, along this arrow, the line is bold. V to this point, this vertex, then this, from here to this, further like this, and here again returning back to the same. So in this manner, you can see that we have traversed through all the vertices of this graph, but two edges had been left untraversed. So in a Hamiltonian circuit, each vertex will be traversed exactly once except the initial one. Edge may be left. For example, here you can see these two edges have not been traversed here. So this is the because this graph is having a Hamiltonian circuit, so such a graph is called a Hamiltonian graph. Hamiltonian graph. And remember, if from a, I shall write the definition in the next subsequent slides here. In fact, if in a Hamiltonian circuit, if I remove just one edge, if I'm removing this one edge, then it is then it remains. We are left with a Hamiltonian path. Similarly, in this graph also you can see if you start from any of the vertex, suppose I mark this vertex as V, and along the bold line if I traverse through it, then I can return back to the same after traversing through all the vertices of this graph. We have traversed through all the vertices of this graph and we have returned back to this. So therefore this is also an example of a Hamiltonian circuit, and in uh, totality this graph is called a Hamiltonian graph. So here as I told you, an Euler graph need not be Hamiltonian. So this I have already explained. This is not Hamiltonian because in this case while forming a circuit you start from one vertex and again you return to A. So we have to traverse this vertex C twice. Therefore it is not a Hamiltonian graph. However, it is an Euler graph. Similarly, here you can also try to find it out how it is not Hamiltonian and it is an Euler graph. Now, one problem was raised by the famous mathematician Hamilton in 1859. What is the necessary and sufficient condition for a connected graph to have a Hamiltonian circuit? So that kind of fixed result was not obtained so far. So this problem is still remains unsolved. The problem was first proposed by Hamilton in 1859. In fact, Hamilton made a regular dodecahedron of wood. Each of, in fact, a dodecahedron has 20 vertices. So each of whose 20 corners were marked with the name of the city. The puzzle was to start from any city and find a route along the edges of the dodecahedron that passes through every city exactly once and return to the city of the origin. The graph of dodecahedron is shown in the figure in the next slide you can see, and one of many such routes is shown by the heavy lines in the next figure we are going to show here. This is in fact the graph of dodecahedron. If you start A, B, C, D, E, F, G, etc., these are the vertices, and these are marked here with the red dots. Now, in this is the dodecahedron, and the question is that is it Hamiltonian? If so, then find the Hamiltonian cycle. So, answer is here. Suppose I am starting from this vertex, then you travel through all the vertices through these bold lines. You will see that all the vertices have been traversed and we can return to the same vertex after traversing through all the vertices exactly once. And in this manner, certain edges have been left. This is one Hamiltonian cycle. This is one Hamiltonian cycle. If you are starting from V, then you can again return back to V by traversing through all the vertices along these bold lines, definitely. So this is one Hamiltonian cycle only. So in this manner, you can find more Hamiltonian cycles. So I leave it to you. Apart from this Hamiltonian cycle, just try to find out another Hamiltonian cycle from this dodecahedron graph. Hamiltonian path, as I explained, if we remove one edge from the Hamiltonian circuit, we are left with a Hamiltonian path. Now two remarks are there. Number one, and this remark two is here. The length of a Hamiltonian path, if exists in a connected graph of n vertices, is n minus 1. The second remark is, in considering the existence of Hamiltonian circuit or path, we need only to consider simple graphs, because the concept of this Hamiltonian circuit or path, we have to consider simple graphs only. This is because a Hamiltonian circuit or path traverses every vertex exactly once. Hence, it cannot include a self loop or parallel edges. Thus, in order to obtain a Hamiltonian circuit or Hamiltonian path from a graph, first we have to remove all the parallel edges and the self loop. Thus, a general graph may be made simple by removing parallel edges and the self loop before looking for a Hamiltonian circuit in it. You can see these are the graphs without Hamiltonian circuits. In these graphs, if you try to find out, you mark any vertex V here and you try to form a Hamiltonian circuit, it will not be possible in these two graphs. So both of these two graphs are examples of graphs without Hamiltonian circuits. Now one question arises. Can you find a general class of graphs which guarantees that it will have a Hamiltonian circuit? So I put the question in this way. What general class of graphs is guaranteed to have a Hamiltonian circuit? So answer is, a complete graphs of degree 3 or more vertices constitute one such class. Means if you have a complete graph of degree 3 or more, then definitely in that graph you will have a Hamiltonian circuit. This is complete graph of degree 3, that means having 3 vertices, complete graph of degree 4, and here you can see this is complete graph of degree 5, that means with 5 vertices. So of course you start from vertex v1, v2, v3. It is automatically very simple circuit v1, v2, and in this way you are getting a Hamiltonian circuit. Similarly here you can also get v1, v2, v3, and let this is v4, and you mark the edges. Suppose I mark this as e1 and this is e2, let this is e3, then I say it is e4, e5 and e6. So these are the 6 edges. You can also find the Hamiltonian circuit in this graph. Suppose you are traveling through, suppose you start at v1, moving through e1, then v2, then through e2 I'm going to v3, and from v3 either if I move through this then we'll return back to v1, but this is not the case. It means I should go along e6. From e6 we have arrived at v4. Then from v4 if we move back to this v1. So in this manner, what was the path you have traversed through? In fact, you have traversed through this, like this here, and here, and here. So in this manner, you have traversed through all the vertices, but all the edges have not been traversed. So in fact, we have obtained a Hamiltonian circuit over here. So similarly, you can also obtain Hamiltonian circuit here in this graph of 5 vertices. So you can try this, and it can have more than one. In fact, here also we can have more than one Hamiltonian circuit. So you can try it. So this is the answer of this question, that all the complete graphs of degree 3 or more vertices constitutes a class of graphs in which you can obtain Hamiltonian circuits. Now about the number of Hamiltonian circuits in a graph. A given graph may contain more than one Hamiltonian circuit. As we have seen, of interest, all the edge disjoint Hamiltonian circuits in a graph, the determination of exact number of edge disjoint Hamiltonian circuits in a graph in general is also an unsolved problem. That means uh, in a given graph, it is not possible to find the exact number of edge disjoint Hamiltonian circuits or paths. So this problem is still unsolved. Now we have two important results regarding the Hamiltonian circuits. In a complete graph with n vertices, there are n minus 1 by 2 edge disjoint Hamiltonian circuits if n is an odd number greater than or equal to 3. So a result is here, but that is not the complete solution of this problem. It has some specific constraints or restriction, because here we are talking about only the complete graph with n vertices. There are n minus 1 by 2 edge disjoint Hamiltonian circuits if n is an odd number greater than or equal to 3. So various restrictions are there. If we have a complete graph with such restrictions, then we can determine the number of edge disjoint Hamiltonian circuits. Then the second theorem is there. A sufficient condition for a simple graph G to have a Hamiltonian circuit is that degree of every vertex in G be at least n by 2, where n is the number of vertices in the graph G. I again repeat, a sufficient condition for a simple graph G to have a Hamiltonian circuit is that the degree of every vertex of G be at least n by 2, where n is the number of vertices in the graph G. So these are two important results regarding the number of Hamiltonian circuits in certain graphs. Now this is an solved exercise you can try, and this exercise based on the Euler circuits, Euler paths, Hamiltonian circuit, Hamiltonian paths, etc. So first one, second, third, these three exercises you can solve, and another exercises of from these exercises 4, 5 and 6 you have to do. You have to determine whether the given graph has a Hamiltonian circuit. If it does, find such circuits. If it does not, give an argument to show why no such circuit exists. So you have to examine all these graphs. In fact, this is not 30. This you can see that this is 7th. 4, 5, 6, 7. So means here we are having 4 graphs. So among these 4 graphs, you have to examine one by one whether these are having a Hamiltonian circuit. If you can find a Hamiltonian circuit, then mark that circuit as I mentioned in the examples in the previous slides. And if it is not having the Hamiltonian circuit, then you should give the argument what is the problem here. So that is it about this lecture, and the content I have consulted from this Nursing Dev. Author is Nursing Dev, and book is Graph Theory and Applications, and the K.H. Roshan's book Discrete Mathematics and its Applications. Thank you.